Do you hear us?
But until now, we can't hear you. No, nothing.
Hello?
Hello.
Now we can hear you.
Hello,
Hello.
good evening. Welcome again with us.
Yeah. Do you hear me? It's okay, it's
Yeah.
fine?
Yes.
Yes. We
Yes.
can hear
Everything
you
is all right.
now. We can hear you now.
Okay. Okay.
Assalamu alaikum.
وعليكم
Walaikum
السلام.
salam.
Hello, everyone.
Hello. How are you?
All good, all good. How are you, see Walid? How are you, see Farid? How are you, Saliha?
Fine,
I'm
fine.
fine. How are
I'm
you,
fine.
Khaled?
Thank you.
All good, thank you. So I am the late today. I am the late one.
No, you are in the time.
Thank you.
You have.
Ah,
Hello everyone.
تحياتنا سي وليد.
كيف الحال؟
الحمد لله.
الحمد لله. أستاذ مخزومي كيف الحال؟
الحمد لله يا
الحمد
خالد.
لله. مرحبا وشكرا على Hello.
We can hear you, Walid. You can talk. Still, we have like maybe 10 minutes to start. So
Yeah, we had the time. Just for the organization of the webinar, I think it's better if we keep the question for the end of the conference.
Okay. Present first, then
Yeah,
question.
let's
Okay.
present first
Okay. Yeah.
yeah. Let's present first the subject, and after that we can make the time for
Yeah.
the question.
yeah. By the way, Farid, Saliha is our vice president, and
Welcome, Saliha.
she will
Thank
be.
you.
I believe she will be moderator today if she wants.
We can be the moderator. The both. It's what.
Maybe she start, but it's to you how to finish.
Yes, I think it's
Oh,
better if you can finish
She
this
has just
session.
one hour at the university, but then she need to
I rely more on Farid.
reach
So
the station.
Yeah.
Farid, save the situation, please.
Yes, this
Farid.
is the
So
point, I
Saliha,
think.
Saliha, she will. No. You are right, Khalid.
Mm-hmm.
You are right.
See, I'm
Yes.
always right. Yeah.
Yeah.
You have the green card.
Yeah. Some people do. Yes. So Farid, normally we will finish today. Yeah.
Yeah.
If
Yeah.
everything
That's
goes
why
normally.
Saliha,
The last part.
she requests to continue first with the presentation, then
Then the
keep the
question.
question to the end. Yeah. Because today I think only we have the multi-rate, and then we have the SIP, selective inflow performance, and then we finish with the presentation.
And
Maybe in the future, maybe you can make like something like with more details. Let's take some subjects.
Okay.
I see your post in LinkedIn about EPER.
mm,
To be honest, I never do interpretation, but I know that's the principle. It's good. I will try maybe
yeah, it's an
explain.
interesting subject. Yes,
Yeah,
it
yeah.
is. Mm-hmm.
It's very interesting. Yeah.
And since we are maybe alone, we can invite you to join our team. Actually, Farid, if you want the SPWLA team.
Yeah. Why not?
Yeah, and we can bring some qalbaloos and baklava. There is no problem.
So you
Online.
drink.
Yeah.
You drink البلوز.
No,
Online.
with fast delivery.
Noon.
Yeah.
No, talabat should be enough. So I believe people still not time. So that's
Yeah.
why maybe there is, people start to come.
الهادي. And
I think you can start sharing your screen.
Okay. So Khalid, we should start, or because now I think 2 minutes or 3
Yeah,
minutes left.
we have 2 minutes.
I believe you have 3 minutes, but maybe we'll do Saliha an introduction for the chapter. So people doesn't know our chapter very well, so we'll take him like 2-3 minutes to introduce the chapter, and then after that, Farid can share his screen and go through the slides. Yes, Farid?
Yeah.
Mhm.
Okay.
Ya Allah ya Karim.
I think we can start now.
Yeah. 1 second.
Okay, welcome to all the participants in the fourth webinar with the SPWA Algeria Chapter. SPWA Algeria Chapter, it's the Society of Petrophysics and Well Logging Analysts. For this chapter is for Algerian petrophysicists. So Mr. Khalid Sidrati is the president of this chapter. I am the vice president of this chapter, and Walid Al-Aib is the secretary. So this is our fourth webinar. We are talking, it's the third session for projection logging, and let's welcome again Mr. Mekhzoumi Farid for the third time with us. And now you can, I think you can start, Mr. Farid.
Oh, okay. Sorry. Okay. 1 second now. Share. So I think the two last session we discussed about PLT sensor tools and also the single phase interpretation, and how to make spinner calibration, and how to process the null velocity and then the single flow rate. Today we will discuss the multi-phase production logging interpretation. Of course, before we start with the processing itself, we need to go through PVT, because we need to understand the PVT properties for the reservoir fluid. After that, we'll discuss the rate calculation for multi-phase, and we give some examples, some real examples. So about the PVT, of course, in any reservoir, we can find three type of fluids: water, oil, and gas. And
Farid,
yeah.
sorry to interrupt. Just for the slides, we cannot see the full screen, so it is it's not
Sorry.
yeah. We want it like full screen.
Okay. Okay, just 1 second. You need to.
Mr. Farid, look down on your right. There is a small icon to click there to make presentation mode.
Okay. Just 1 second. Windows. I want because I share. Okay. Just 1 second. Let's take this one. I mean, now it's okay.
Yeah, much better. Yes.
Much better.
Mm-hmm.
Thank you.
It's full screen now.
It's full screen, yeah.
Yeah.
Yes.
Yeah.
Okay. So now we continue. So we will go briefly through the PVC properties for reservoir fluid, because we need this in our interpretation for production logging. So we have gas, oil, and water in any reservoir. Okay, of course, the specific hydrocarbon produced depend on the reservoir pressure and temperature, because we have downhole pressure and temperature. We have surface or standard pressure and temperature, which we can, make the well test, surface well test measurement. Because our tool is measuring downhole, so we need to convert any like the specific gas gravity or oil gravity from surface condition to downhole condition. So for that, of course, we need PVT. So here we know that if we have hydrocarbon, let's say we have oil, always inside the oil we have soluble gas inside in it. So we have like, if we have like pressure and temperature which load the all gas to be solved inside the oil. So at downhole condition we get like one phase. It's if the two phase are together. I mean, like in let's say in case of light oil, we have solution GOR. We have gas which is solved inside the oil. So it's forming one phase. But one, you have like drop in pressure and in temperature, some gas start getting out from the oil, and then even downhole we can get two phases in this case. So we need to know this pressure, or what we call saturated pressure, bubble pressure, or dew point pressure for the hydrocarbon. So it's very critical for our interpretation. It's make like big difference. If you put wrong bubble point pressure or dew point pressure, so you cannot get something much with the well test surface measurement. So of course pressure, because we have here for the PVT we have three things: pressure, volume, and temperature. Of course, from bottom to surface there is a huge change between pressure and temperature. And also the volume itself, it will be different. So any because for the fluid phase, it depends on the gas and also on the pressure. So as explained it before, for example, such for light oil, we need to know the bubble point. Let's say for condensate gas, we need to know the dew point pressure to get, because for our tool, we are measuring, let's say, the tool which we can get the hold up, it's the density or either the capacitance. Let's take the case of density. The density tool, it's giving a mixture density. Let's say we have two phases, it's mixed together, gas and oil flowing together. So our tool, it will give us the mixture density. Now, how we can get the holdup? I mean, the percent for each phase. Let's say I have oil and gas downhole flowing together, and I want to know how much oil and how much gas. So for this, I need PVT properties. I need to know gas specific gravity at standard condition, and also oil specific gravity at standard condition. For that, I need to convert this oil and gas and to know for every phase downhole at the same condition what I am measuring with my tool. And also that's why we are running pressure sensor and temperature to know the downhole pressure and the downhole temperature. And through the PVT model or correlation, I convert what I have for value for standard condition for gas and oil, gas gravity and oil gravity, to the downhole condition. And after that, I can get my holdup from my mixture density. So somehow it's not only the measurement which we get from density, because the density doesn't give us direct holdup. I know there is some tools in the market which give you the holdup. It's another, we can discuss it later. But what we have as standard MPLT, standard production logging, the density itself, it give us mixture density. So for that, we need to know the pressure and temperature downhole, which we can get it from PLT itself. But to convert the value for oil and gas at downhole condition, we need the PVT properties, which is like separate test. They take sample, downhole sample, and then they make the PVT test to get a bubble point dew point, and to get also as well the formation volume factor for which we will discuss it later for gas and oil, BU, BG, and BW for water. So of course, here pressure against temperature keeping the volume constant, pressure against volume keeping the temperature constant. So it's the basics of PVT test. I mean, you have like here, like you have two phase which is like mixed together, and then you apply high pressure and high temperature. You keep small volume. When you release the pressure, because we have some gas is start going out, take expansion, then you have like more volume till we reach like bubble point pressure. Then we start getting the first bubble of gas, and at the end the last bubble, and then you can get gas only. So the relationship it's between pressure and volume. This is our case because at downhole we have high pressure, high temperature, but once the flow it's flowing to surface, we have drop in pressure and in temperature. Then the state of the flow itself it changed, the phases it changed. And of course, here we have this chart pressure and temperature, and we have what we call critical point. Here, for example, we have only liquid because we have high pressure. Also we have high temperature, and this one what they call vapor pressure curve, or saturated pressure, or for oil, light oil, it's bubble point. For condensate gas, it's like dew point. And then here we have the critical. Here you see, for example, if you have like in this case, you have like dry gas, even you increase the pressure, it's to remain the same. So for our interpretation, we need this PVT correlation and PVT modeling to get the right things down.
Farid, can I ask here a question?
Yeah.
Just for the PVT, the time when we acquire PVT usually is in the beginning of the well or something like that, like to do reservoir study. So
Yeah.
if we are doing this job after too many years, after this well has been producing and everything, so formation fluids will be, how to say, slightly different, or maybe largely different. We don't know. So how we can rely on this PVT without any correction, or is there any like how to say
Yeah.
way to mitigate this problem?
Yeah. That's true. This is big challenge. Even most of the companies are not doing PVT for every well, which is not possible. Usually they do it by area. And sometimes normally if there is no like let's say, because we face this one mainly in Hassim Saud, because we have we inject gas to maintain the pressure, and this gas mainly is not from Hassim Saud field. Sometimes it's from another field. You get my point? So even for the properties it's completely different. And when we produce, sometimes we have free downhole gas, which is coming mainly from the oil, because it's depleted reservoir. And also we have another type of gas which is coming completely from another field, sometimes from Gassituil, sometimes from, it's not from Hassim Saud. What they inject in the reservoir is not all the gas is coming, because Hassim Saud it's light oil. So that's true, because here even, I mean, it's not easy. It's not only you have like one gas, you have two gas. So here you need somehow how to constrain your PVT model in your software. Sometimes to get value in between to get your results matching with I mean with this two type of gas. And also as well, sometimes even if they only have one PVT study in the whole field, they don't make it for different I mean zone. Sometimes we get it, we can see it when we make the interpretation. You don't have the right matching, unless if you have like segregated. Sometimes you are lucky in shutting survey if you have like segregated phases. I mean, you have oil. If you don't have cross flow, let's well, you don't have any cross flow, and you have like gas and oil, it's segregated down. And in this case, you can take directly, because now you have your oil separates and your gas separates. and you have your pressure temperature, and then you can use this value to constrain your PVT model. You get my
Okay, thank you, Farid. Yes,
yeah.
it's fair enough.
Sometimes you need to use the shutting data. If you have like, because what from PVT what we are looking for, we are looking to convert the surface density for gas, oil, or water, whatever, to downhole density, to downhole condition. So if you have like segregated phases already in shutting conditions, so you have the value directly. Let's say if you're in your PVT, you enter the PVT, what you get like from the field, but you get like, for example, let's say your downhole density for oil, it's let's say 0.65 from the PVT model. But in reality, you have segregated oil during shutting condition, and it's, let's say, for example, it's 0.56. So in this case, only you can constrain that you say no, instead of 0.65, no, it's 0.56.
I
Yeah,
see.
you
Yeah,
constrain
thank you,
your
Farid.
PVT
Thank you.
models. So we can continue now. This is what we call phase diagram, single component. So this one, it's for different temperature and for different pressure. And here, of course, this experiment, there is a line between, for example, your phase, like from gas to convert to liquid. If it's above the saturation pressure, let's say dew point pressure or oil point pressure, and vice versa. Also, if you have like liquid, it's transformed to gas when you have less pressure. But of course, you have like critical points, like in this area, we can see, for example, for the gas, it's stay all the way in the gas. And like there is like boundary between this critical point here and liquid here. And I have experienced that some wells, when it's coming in this area, it would be like to classify, it will be like somehow, challenging to get the right, to put the right PVT here. So this one, it's how this one is for single component, this one is for multi-component. So we can see this graph, it's almost the same this one. But for example, let's see here, if you have like gas, and this one what we call a dew point curve. This one is the limit, it's dew point pressure. It means you have like pressure. If you are, below this pressure, you have only one phase. If you exceed this pressure, you start getting like liquid and gas, and like it's per percent, till we reach here the bubble point pressure, and here you get only liquid. Let's, for example, in this case, we have point A and point B. Even we have a drop in the pressure. If let's say this is my downhole condition, A and B. But like here, I still have one phase. All my gas, it's inside the oil. It's forming like one phase. It's two components, but it's with the pressure and temperature, it's keep like one phase. It's all inside. But when we exceed the bubble point, we have less pressure than bubble point curve, we start getting separation, getting some gas out from the oil. So that's why it's, pressure. That's why we run the pressure and temperature sensor in the production logging to get the downhole pressure and temperature to use with the PVT model, which we get PVT data, which we get, and from this we can process that we have oil and gas, or only we have oil. You have like free gas, downhole free gas, or you don't have downhole free gas. It depends what you put here. So it depends on your bubble point. So if you give as input wrong bubble point in your model, so it gives you, of course, wrong results. And this one is not depend on the production logging measurement itself, but because it's related to the PVT. So that's why the PVT also, it's important to get the right PVT and to check it before to get your final interpretation. So let's see here, for example, for this phase diagram for condensate gas, and you can see here from A to B, you still have like one phase, it's condensate. But once, for example, let's say, for example, another example, CD, it's almost the same. But if it's moving inside this envelope, here it's meaning you start getting two phases: oil, condensate itself, and gas. Because in condensate gas, it's the oil which is inside the gas. So getting less pressure, less temperature, and start getting condensate coming out from the gas. The previous example is for light oil. This one is for the dry gas. Also, it's stay here. It's the same case. This one is for gas, but only the volume is changing. So you stay in this area. So this one is summarize this phase diagram for all type of hydrocarbon. So in this side, you still have dry gas, even you have drop in the pressure, but you only have dry gas, because dry gas there is no liquid in it. You get the same. Here we have like condensate gas, and what we call critical point. From this point you start, when you cross it, you start getting liquid and gas. Here in this envelope is wet gas. Pressure it's less than PA, and critical pressure. And here is the volatile oil. That's why I tell you this boundary. Sometimes you have volatile oil, what we call light oil, and you have gas condensate. Somehow it's happened to me one time I have went to interpret to make interpretation, and they classified as gas condensate. But when I apply the gas condensate model in my interpretation, and they take the PVT as gas condensate, I never get much with the surface well test. Now the difference, it was huge, because they have, let's say, about 600 metric per day of oil condensate. Myself, when I use gas condensate, I get only half of that. So there is something wrong, and I try to fix it. When I go and I check all the parameters from PVT, I see that GOR, it's more indicate that it's like volatile oil, it's not gas condensate, because for hydrocarbon classification, it depends on the GOR and the pressure also. You have like black oil, volatile oil, gas condensate. How much GOR to classify your hydrocarbon? What type? So once I change to volatile oil, and they put as volatile oil model and PVT, directly I get matching perfect with the surface well test. So because it's the same data from the production logging itself. I don't change anything, just to choose the right model. So to understand PVT and to choose the right model. Even they classify as gas condensate. When they give me the well, they say me it's condensate, gas condensate well. But after that is not, because it was in this area, in the critical boundary, this one. So just when I change, it's much. So here is the black oil, and here is solution.
If you don't mind, I have a question.
Yeah.
What is the ratio if you want to distinguish between these two types, the gas condensate and volatile oil? For example, on the result, what are the characteristics of GOR for each one?
Yeah. Here GOR, it's very high. You get it, it's very high compared to here. But the problem when it's closed in this boundary, it's like small difference. Because we can go back to the classification of hydrocarbon. I think there's like some standard. They say, for example, for black oil, you get this GOR, I think, between 0 something to, I don't know, less than small value. Yeah, maybe I can look for this classification. For volatile, you have like more gas also with oil, but GOR, it's less compared with gas condensate. So that's why. And also, it's not only this, and also the specific gravity for gas and let's say in condensate, for example, the API usually found it's 56, 55 degree API, something like this. Volatile, you can get it less, 52, 48. Because yeah, there is, the classification of hydrocarbon, it depends on the specific gravity, GOR. This is the two main things which you can classify. This is gas condensate or volatile oil. But the problem here, what I want to mention, when you have something close to this boundary, because
Yes.
only it's like it's line between the two zones. So here, either you see, for example, maybe GOR is closed each other, but if you see, for example, the specific gravity of oil, let's say, usually we know that's condensate, usually it's like high number 50, more than 52, more than 50, 55, 56, sometimes 57. But if you go less in degree API, let's say 48, 50, so we are more close to the volatile area.
Thank you.
Yeah, sorry. Curve, pressure, temperature, trajectory at which saturated vapor start to condensate. That's why, because here for gas condensate, it's like vapor of liquid start to condensate. Bubble point curve is the pressure, temperature, trajectory at which the liquid start to boil. I mean, liquids start coming, gas start coming from liquid. And the critical point is the point where the bubble point and dew point curves meet. So we are thinking about this line. Yeah. So that's here to classify to know which type it's make like big difference. Okay. So, just a second. It's going wrong. Yeah. So also here there is another important parameter is the formation volume factor, because we know that's oil. Let's say if we have oil and the gas, it's solved inside the gold, inside the oil. So when we have less pressure, when we cross the bubble point pressure, we start getting oil and the gas is coming out. Because here it's like reservoir condition. We have this much of oil and this gas, because it's with pressure, and we have water. So surface condition, we have oil and we have more gas and we have water. It's almost the same, but sometimes only we have what we call WGR. We have like some gas, it's solid inside water. So here we have solution GOR, and here we have like solution GOR with for water. So formation volume factor, it's to convert from downhole to surface, or the inverse from surface to downhole, because we have this any fluid volume at reservoir condition divided by fluid volume at standard condition or surface condition. Because standard condition is at atmospheric pressure and 15 degree Celsius. So here we the abbreviation it's B. The name is like formation volume factor. So we need this one to convert from surface to because even for production logging, when we make our interpretation is downhole. So if we want to know in standard condition and to compare it with the well test, we need to convert it. So we use the formation volume factor. So this one is for the retrograde gas condensate. We have this much of gas, and then we have the BG, and we have, of course, gas liquid ratio, usually between oil and gas, or maybe if you have oil, water, and gas. And after that, you have like condensate when your liquid come out from the gas. So this is the difference between, volatile oil and condensate, gas condensate. And for the interpretation, you need to choose your model. You need to choose either it's condensate or either it's volatile oil. Why? Because the PVT it's somewhat different, because here you need to give a dew point pressure and here it's bubble point pressure, so it's not the same way how you can convert from surface from downhole to surface. So that's why I give you this example. When I take as gas condensate, I don't get much in the results with the well test, because when when it's converted to standard condition or surface condition, it never, because I'm taking the wrong model. Just once I take the right model, because it was like volatile oil, then I get everything is patching. So this is like some examples of value for oil. Usually you can get it from 1.2 to 2.4. It depends on the oil specific gravity, how light it's your oil or how heavy it's your oil with another mark. And also gas, it's always this number. Let's say for gas condensates, it's around this number. And it's it's unitless because it's either meter cube divided by meter cube or either like barrel per barrel. So it's like it's the factor. So this is an example from Emerald Square. This is the PVC modeling. And here you have option. You can just what we discussed before, Khalid. You can constraint because it's the same. Let's say if I have my value, like here, for example, you see like red dot because I have the value from the shutting. So I can constraint my model. This is the good things when you have shutting and you have like phase segregation. You have your downhole density of oil, downhole density of water, downhole density of gas. Then you can constrain your PVT model. So this is also for bubble point. This one is for solution JWR. This one is for bubble point. And this is also for view, formation volume factor for oil. This is also viscosity, which enters somehow in to get like the density, downhole density, and all these things. And this is the downhole density also. You can match, you can constrain as well. So all these parameters we need it for the multi-phase. And also it's very important because we have like, let's say if you make multi-phase interpretation, I can say maybe 50% of for the accuracy of the processing of the results, 50% from the sensor, I mean data itself from PLT, and 50% it's from PVT. If you get wrong PVT, you never get right, accurate results. So here we start with the multi-phase rate calculation, how to calculate. Because last time you know that we calculate the gross. I have the downhole velocity, the mixture velocity, VM, which we discussed in our previous presentation. So for the gross or for the total, I have. So now only we need to split by phase. So multi-phase flow, it's phase velocity. So I need to know the phase velocity. So last time, you know, that's only we have one velocity. It's the average velocity for the mixture. I don't have, for example, for gas, how much. We know that's now, let's say for the horizontal work, because we have like stratified flow, we have for gas, for oil, for water. But here I need to know the phase velocity and the phase area. So when we talk about phase area, it means how much, for example, let's say if I have oil and gas flowing together, how much the oil is occupying area in the pipe and how much also the gas is occupying the area from the pipe. It's like percentage or hold up percent. And also how much the velocity of gas and how much velocity of oil. That's what I need to get multi-phase flow. But of course, in reality, we are measuring only one velocity because our tool, what we have here, this is the average velocity corrected VM, because we have apparent, which we corrected for the flow profile. So we have VM, the average one. And here, because of course we have the diameter area. So here, let's say this is a portion of water and this is a portion of oil. In this case, for example, I have heavy phase, it's water, and light phase is oil. This one is like imaginary condition. It's not, in reality, everything is mixed together. But what I have velocity from oil and velocity from water. So you see in this example, I make velocity, the arrow for velocity of oil, it's like higher, much higher than the water. Because here we are in the vertical well, and the oil, it's lighter than water. So the oil, it's moving up quickly, relatively compared to the water. So it's like we have these two velocities. So let's talk about some definition. So hold up, because sometimes we hear also water cut or hold up. Let's say in this case we have hold up. What means the holdup? Is the area fraction of the pipe occupied by the phase of interest. Let's say in this case, if for example I make separation between oil and water, so I will calculate this quantity of oil, how much area it will occupy from my pipe. So this is the holdup. And also for the for oil is the same things. So for oil, water, we give by definition hold up, it's y. Y, when you see y water, it means hold up of water plus hold up of oil. It's the whole pipe area. It's one. Oil, water, gas flow. We have three. We have water, oil, and gas. So the assumption of the three, it's one. It's give me the whole area. Now let's, for example, we have this definition of water cut. Cut is the ratio of flow rate. For instance, in oil water flow, or usually we use this word in oil water flow, we can say water cut. And the water cut is the percentage. It's water rate divided by the gross rate, I mean oil and water. So this is the water rate. But usually when we calculate the water cut, it's on the surface, at surface, when we make separation. But in the flowing condition, let's say, for example, you have a well and you have the well tests results, and they give you less. Okay, we get, for example, 30% water cut, 30% water cut. But you run with our PLT downhole, and we get in some cases maybe that's the water maybe it's taking 70%. So the hold up, it's things related to the flowing movement. Water cut, it's after separation at the surface. When we separate the two phases and we get this percentage oil and this percentage let's say take volume, and then we separate this volume. But hold up, you can get, for example, well with 30% water cut, but maybe downhole sometimes you get like 70% hold up of water, and sometimes maybe you get 5%. Because the hold up, it depends also on the velocity of each phase. So we can summarize as the hold up, it's dynamic. It's when you have two phases flowing together dynamically. I mean, here we can talk about hold up. But when you talk about water cut, it means after at the surface when you make separation. So just to get like to highlight these things, because there is difference between, you can get like water hold up is not matching with your water cut, because water cut we take it at the surface after when you separate the two phases. Also, we have another term here, what we call superficial velocity. This one is not real velocity. We are going to talk about it, and also it's very, very important to solve our question here, because our tool, it's measuring one velocity. It's not measuring like gas velocity, phase velocity, I mean gas, oil, and water. So they bring this superficial velocity. It's is not real velocity. It's like imagination velocity. We put it to solve the question later on. So what means superficial velocity is the velocity that a phase would have if it's alone flowed in the pipe. It means that's here. Imagine that we don't. Okay, I have this much of water. Let's say, for example, this hold up, it's 25%. But let's take, imagine that's only, I have this 25 flowing alone in the whole pipe. So this is the idea of the superficial velocity. The sum of the superficial velocities is equal to the main velocity. What means? VSH, I mean here H, it's for heavy phase, in our case for water, and L, it's for light phase. Light phase, it's oil. So the summation of superficial velocity of, let's say in our case for water, which is heavy, plus light, it's give me this one here. And also now, in reality, what we have, when you have two phases flowing together in a vertical well, heavy and light, in our case water and oil, so we have what we call slip velocity or slippage velocity. This is the absolute velocity difference between phase flowing together. It means the difference between oil and water. And as we said before, because oil it's lighter, so it's moving faster than the water because it's heavy, because we have gravity, because water is tend to fall down due to the weight, due to the density of weight of water, because we have gravity. The gravity it's acting on both, but here because we have heavy, it's tend to do to go down and is not flowing faster as oil. So the difference between these two velocity, we call it slippage velocity. So slippage velocity, as definition, it's the light velocity minus the heavy velocity, because the light phase velocity, it's always faster or more than the heavy phase velocity. So keep this one. We have superficial velocity of heavy and light. It's equal to Vn. This one we get it from the tool, and of course we get it from the spinner after calibration. We know this all these steps. And here we have the slippage velocity. It's light velocity minus heavy velocity. So for this slippage velocity, it depends also as well on the flow regime. So there is now like there is no direct equation to define or to calculate this slippage velocity. So for that, we have what we call correlation. Some correlation they was made, I mean, in the lab, they take like different phases with different hold up. So that's why I tell you even before, that's the hold up. It depends also on the flow regime. And also for some cases with different deviation angle, it's not like completely vertical, and they come like with some chart which give you the slippage velocity. So in the SD3, there are like many which we use in in the production logging interpretation. So here we have, I mean, some definition about hold up. So I think now everyone understands what is hold up and what the difference, for example, let's say between water hold up and water cut, something too different. And also we have this superficial velocity, which is not real velocity. It's only from imagination to solve the equation, because these two, it gives us the total velocity, which gets it from the two, and also the slippage velocity from the correlation. So here, let's talk about now, because we have this relation between, I mean, velocity and flow regime. So in our case, let's take bubble flow regime. It means the main phase. In this case, it's like, let's say, for example, we have oil and bubbles or drop of water inside, or vice versa. When you make like separate, so we have this one, it's for velocity of water, and here we have what we call hold up Y water. It's the percentage. So, and also we have the area. This is the pipe area. So I take the percentage of water times the pipe area. It gives you the area occupied by water, and this is the velocity. And also here I have now, because we know that's when we sum hold up, oil hold up, and water hold up, it gives me 1. So I can take instead of, I take the, because this one is hold up of oil, YO, so I can take 1 minus Y water, because now I need to solve equation. That's why we make this activity. Area is the same times the area is the same area, pipe area, and velocity of oil. It's what, because before we say that slippage velocity is the difference between heavy and light. So here, oil velocity, it's the water velocity plus slippage velocity. So heavy, light, this one superficial velocity, sorry, superficial velocity, if we can come back to the other slide. So, and also here now, we have heavy, let's say in our case, for example, water here, and here light, it's oil. So here what we have hold up of heavy phase. Here it's the volume, or let's density of heavy phase divided by water. Is the water density divided by water and gas, and the other way around. So here it's H for heavy. When you put any, when you see in this presentation, H, it means for heavy phase, and L is for light phase. So we discussed it before. The holdup of heavy and light, it's 1 when we take the whole unit system. So how now we calculate the holdup from the density? It's almost the same way how we calculate shale volume from the gamma ray. Somewhat is the same. So this one is holdup of the light phase times the density of the light phase. But which density? This one which we get it from the PVT data. When I get, let's say, a gas specific gravity or oil specific gravity or water density at surface. So this one, but this one is not from the surface. This one we convert it at the downhole condition. So I have the percentage of light phase times the density of light phase plus the percentage of heavy phase times the density of I think it's by mistake, heavy phase times density of, normally it's heavy phase. So this one is only by mistake. It's give you the mixture density, which we get it from the density tool. So if I can get the holdup, so I can get it. Because now heavy and light, it's the total. So now how we calculate? Let's say for here holdup of heavy, if we have like water here, it's mixture density from the tool. Let's say, for example, my tool is give me 0.9, and I know that's in my well I have oil and water. And my, let's say my water density it's 1.1, and my oil density, let's say it's 0.65, for example. So 0.9, it's give you also an indication that you have like more water because it's in between. Because if only you have water, you get 1.1. If you have only oil, you get 0.65. So you have 0.9. It's like for the gamma ray, you have like a clean and shady zone, and then you calculate the percentage. So it's the mixture density minus the light phase density over divided by heavy minus light. So this heavy minus light, this one what we get from the PVT when I convert my gas gravity or oil gravity or water density from surface to downhole condition at the same, I mean, condition of my well where I'm doing my PLT, my production logging. So now it's for this downhole condition. What I use PVT as we discussed it before. But what I take from my tool, I take pressure and temperature. I need to know the downhole density of each phase in this pressure and this temperature. So that's why I tell you that's the accuracy or the results from PLT is depend on the sensor PLT itself, which we can control, and also from PVT. So in some cases, if you don't put the right PVT, the accurate PVT, you get the wrong results because it's like is an input. So here we get the heavy phase. So since we know that's heavy phase plus light phase holdup, it's 1. Only we need to solve this equation if we get only the heavy phase or light phase. So it's solved. So for two phase here, it's more simple. So let's talk first of all about two phase equal velocity. So here we assume that's the two phases have equal velocity. I mean, when you say equal velocities, it means you don't have steepage velocity. So what we have here, because what we want to say that's flowing the same velocity would be sufficient to have bulk rate and the way of measuring the holdup. So here we have this total rate, which we discussed it last time for the gross rate. This one, it's only for this V apparent. This one is the VM, because we have this velocity profile correction factor, 0.83, which we talked about it in our previous presentation. And here it's to only convert convert factor for the units. And here is the diameter, pipe diameter. So here you get barrel a day, and VM is feet per minute, D it's in inch. So here we have density, which we get it from the tool. It's the holdup of heavy phase times density of heavy phase plus light times the density of light phase. This is the total because I get This one is the I get it from density. So this is the mixture density. So this is my holdup, what we say. And also now, if we want to convert it to the rate, so heavy phase rate, it's holdup of heavy phase times the total or gross rate, which we get it initially from the spinner. And here the light is the same thing. So because the light it's total minus heavy. So once I get one rate, I get the second one. So this one is for the two phases without slippage. And also here, because hold up always is the same. Now we have these rates, which we get it before. Now let's make this slippage velocity. What we call about slippage velocity? It's light minus heavy, because we say always the light, it's more than the heavy phase. So this is the slippage velocity. And now if we try to convert the velocity on by rate, now we have this rate of light phase, and we have this velocity because we have the areas, the same area pipe, but we need to multiply by percentage the holdup of light phase. So we make this substitution, and we get at the end after we get the slippage velocity is this equation. It's the light rate, the light rate of the light phase minus the rate of the heavy phase over the area of the pipe times 1 minus holdup of heavy phase, and minus the heavy phase area. This one is like math, it's equation. You can even when I share with you the presentation, you can also go through it by yourself. That's why I just here to see how the model it's work for to get two phases or three phases, and what the meanings of slippage velocity and what meanings of holdup, all these things to understand what's going on. So rearranging, of course, and then we get this one because here, let's say for two phase, we need only to know one phase. Let's say, for example, here for heavy phase rate, it's the holdup, and also for total, this Q total, we get it already from the spinner, from VM. We know total, whatever. For example, I have velocity because what I need to get to know the Q total rate, total rate, I need to know area pipe, and I need to know the velocity, because rate it's velocity times area. So this one I get it from the tool. Okay, this one also we get it from the from density, of course, with the input of the PVT to get the right number. Also, this one I have it, and this one is only about conversation. Now only this VS, this one, this slippage velocity. So this is the equation. So that's why here we need correlation to know the slippage velocity, because it's not something which we can calculate. So this one is because this one now the last time, okay, because it's equal velocity, so VS is like 0, no problem. So this one unequal velocities. If we have like two different velocities, of course we start with the same equation for the rate. Here we have VM, which you get from the tool, and here it's only the pipe diameter, and this one is only for unit conversion. So it's here it's mainly velocity times area, simply. So the rate, the gross rate or total rate, I get it directly from the tool. Now, of course, here we have same for this holdup, which the measured from the tool minus light phase density over heavy minus light. This one I get it from the PVT when I make conversion from surface condition to downhole condition using this formation volume factor, everything. So I get my holdup for heavy phase. And when I get heavy phase, I can get light phase because YH plus YL equal 1. So it's like one unit system. So also it is the same things, because here we have this slippage velocity unequal. You have slippage velocity in this case. Now phase velocities, we want to see what's this is between the light and the heavy. So the average velocity of each phase So it's the, I mean, VH, heavy phase, it's the rate of heavy phase over hold up times area. Okay, this one's for the light phase. It's the pipe area, of course. Now the summation of two hold ups, it's equal one. So assuming average velocity are equal. Now just for like assumption, we assume that's VH and VL equal to each other. So we make this equation. I mean, what we have here. So we get rate, heavy phase rate over divided by light phase rate equal hold up of heavy phase divided by hold up light phase. So we have this one. Okay. So now we come back to this definition of superficial velocity. Superficial velocity of given phase is the rate of the phase divided by the pipe area. It's mean we take the let's say even I have 25%, but I imagine that's the this phase it's flowing alone in the whole pipe area. This is the meaning of superficial velocity. So it's like even this one I have 25%, but it's like flowing all in the whole area, pipe area, and also for what? For I mean heavy and light. Let's say. So superficial heavy velocity. It's now that's the definition by equation. Superficial heavy, it's the rate of heavy phase divided by the whole pipe. That's what we say now. And also for the light is the same things. It's the rate of the light phase divided by the whole pipe. So the total of the superficial velocities is mixture velocity. We know that's VSH and VSL as we defined it before. It's VM, which we get it from the two. So VM equal rate heavy rate plus the light rate divided by the area pipe. Now heavy phase velocity, it's coming VH, because now we're looking, there is a difference between superficial heavy and the heavy velocity. This one is the real velocity. I mean, one have like heavy phase velocity and light phase velocity. So it's the heavy phase rate divided by hold up of heavy phase times the area, the pipe section. And the light velocity is the same thing. Now, sorry, just go back. Yeah. So VH, because when we compare things, it's superficial velocity divided by hold up of heavy phase, and VL, it's the superficial velocity of light phase divided by hold up of light phase. This one is the combination, because now only this one is like by definition. Just we use it to solve the equation. So if we want to present this slippage velocity in graph type or chart, let's say here we have the holder from 0 to 1. Let's see in our case, for example, any holder. I mean, here, for example, it's because the hold up is from 0 to 1. So here I have YH for heavy phase, and here I have mixture velocity VM, which you get it from 2. So, and here I have this line, which is the relation between hold up and velocity. I mean average velocity. So if we make this graph, we get like something like linear, and this one it's representing the superficial velocity of heavy phase, and this one it's superficial velocity of light phase, VSL and VSH. So because why? Because we say that's the sum of them, it's equal to VM. So this one with equal, I mean, there is no slippage velocity with equal velocity. There is no, I mean, there is no slippage velocity between heavy and light phase. And also, since the holdup we get it from, I mean, from the density. So this one is the density of light phase, and this is the density of heavy phase. Because if I get like 100%, it means I have here heavy phase. So H1, because here it's heavy phase holdup. So if I have one, it means, let's say, now, if we take, for example, oil and water, if I have 100% water, I mean, I have 1.1 gram per cc, it means I have only water here. So here water is coming, here it's VM, so I have the whole thing, it's water. If I take in the middle, I have, this is the density from the joule, it's mixture. Let's say here I have, if I have oil, let's say, if I have oil 0.6, for example, and I have water, it's 1. So in between, if I have any density of 0.9, 0.8, which means it means mixture between oil and density. So if I take it here, it means this one, this part is for heavy phase, let's say. If you have water here, it's superficial velocity of water, and this one is superficial velocity of oil, because the sum of the two, it's the VM, which we get it from the two.
Farid, can I ask a
Yes.
question here, please?
Yeah.
Yeah, just for the mixture density, we measure it with the tool, yes?
Tool, yeah.
Yeah. So when we have a two-system fluid, like let's say we have like oil and gas
Yeah.
flowing together, but it's the flow regime is like how to say
Slugging.
an
Slugging
annular
flow
flow or
regime.
something or slugging. So this density measurement will be somehow wrong. So how we
No,
can
that's
rely
that.
on this?
Yeah, exactly. Khaled.
Mhm.
Thank you to highlight that. That's why also we connected the hold up with the flow regime. So you know that's to make like good interpretation, or to get like ideal condition. You know, like stable, well condition, and you know like stable, well flow regime. And the most like, it's like turbulent flow or bubble flow. Sometimes like froth or like slugging flow, it's difficult unless if like you take like average from different passes and to get like overall picture profile. You cannot get something accurate with slugging flow regime. It's not easy,
And
because in this case sometimes,
mhm.
because your tool is reading completely water, and sometimes it's completely reading gas or
And can we rely on the density derived from the pressure in this case, or
yeah, no, yeah,
Mhm.
for yeah, because last time for the sensor we are not because you know, because my idea is to present everything in one go, is to get an idea. Maybe later on we can make like different subjects and we can go like with more details. Yes, for the derivative only have the friction effect, which is like correction for it. That's it. You can use, yeah, from density only. Also, if you have like deviation, because derivative have limitation till I think 60 degree. Over 60 degree, you cannot correct for deviation.
I see. Yeah.
Yeah,
Thank you
yeah.
for
So
it.
you have two things for derivative from pressure or gradient. We have the friction effects of the flow and the pressure sensor itself, which need to be corrected. There is like some correction chart, and also the deviation.
I
Because
see.
here just we want to give the whole process of the production logging, starting from sensor and how it's working, single phase, multi-phase, because we cannot go more deep, but just to get to give an overlook for the whole process. So that's why now, for example, for multi-phase, it starts coming like slightly complicated compared with the single phase. And also, what I want to highlight it here, what's the parts from the tool, which we can take control, what's the parts from the PVT, because this is the tricky things. Because some people, they think that's only you have the data and you have to give me the right results. It's not, I mean, I cannot, it's not straightforward, but you need to know the process, and you need to also to know in which parameter you are confident and in which you are not. Like here in our case, I can tell you, for example, till we get the downhole velocity, it's easy. Spinner, we discuss it, how it's work. You have slope, you have a threshold, خلاص. Since you get your apparent velocity, then you can correct it for I mean, what we call velocity profile correction factor, and that's it. When you get your velocity and you have your pipe area, or you have caliper, what you can get your diameter, you can get your total rate, gross rate. Now we are discussing how to split, because we are using density, but density to calculate the hold up, we need PVT to know the downhole density. Unless if, let's say, you have like segregated phase in shutting condition, then you are lucky. You can constrain your PVT model. Now you have like something which you can trust. You are measuring, for example, from PVT, I get my downhole density, let's say, at for example, 100 bar, and let's say at 120 degrees Celsius, I get from PVT modeling, I get, for example, 0.6. But in reality, when I run with my tool, I get oil phase, and I get, for example, is 0.65. So we can correct.
Fair enough. Yeah. Thank
Yeah.
you, Farid. Yeah.
Okay. So now this graph, it's like now we don't have right now it's like we don't have the slippage velocity effect. Now let's say, for example, in this case, if for example also here because I have velocity, I can make it rate. Because if I have the pipe area, here I can make it rate. Let's say, for example, here I have 50 meter cube a day rate of water and 50 meter cube a day rate of oil. That's what we get if we don't have slippage velocity. Now the whole picture will be completely different when we have the slippage velocity. And this is the big, I cannot say it's, I mean, because slippage velocity also is related to the flow regime. Flow regime also is dependent on the velocity. So that's why they use this correlation. Some correlation are made in lab. They put really like different phases in a pipe with different angle and different pressure, and then they try to generate like chart to know in this flow regime we can get this slippage velocity, in this flow regime we can get that. So okay, now let's move. Okay, we have seen the slippage velocity. So now this is in the graph. We see before it's like here straight line. What's happened? Because what we say let's take this slippage velocity to make it like, to imagine it how what's happened. It's like, let's say one fat guy with heavy guy, I mean, have like overweight, and one guy is like small guy running together. That at the same, so because always let's say for light phase, it's like this guy who is like less weight and he can move faster. The other one, he moved, I mean, slowly, not fast as the other guy. It's the same things. The light phase is moving faster. The heavy phase, why? Because the gravity, mainly in the vertical. All these things we cannot get it in a horizontal well. In a horizontal well, because we have like the flow regime, it's like clear, it's stratified flow regime. We have segregation because we have gas at the top, oil in the middle, and water in the bottom of side of the hole. But here, because everything is like in the vertical well, so that's why, if for example, for the same case, if I don't take the slippage velocity and I make my interpretation, because as we say that's VM here, it's rate. So what I have, if I take this projection of the same density, I have mixture here and I put it here. You see how much difference here? But in reality, because I have this slippage velocity, that's only have this much of water, for example, of heavy phase. But if I ignore the slippage velocity and I mean project my mixture density to cross this line, so I get in this case the heavy phase, all this one, let's say. So you see the difference? So that's why it depends on the slippage velocity and the flow regime itself. That's why here the relation becomes nonlinear due to the slippage velocity. Because before it was linear, now it's nonlinear because we have the slippage velocity. Regime between the two phases. So now we convert this one to the rate because we say that's VM velocity or rate. It's the same since we're having the area pipe or the whole area. No problem. So that's what we have here. This one VSH is superficial heavy velocity. What we say, it's the rate of heavy divided by the whole area of the pipe. light superficial light velocity, also it's the rate light velocity divided by the whole pipe area. The VM, only this VM we have it from the tool. All this one is something to solve this equation. So we have the total rate divided by area, of course. So this one and this one, it's VM, because as I have seen before, the VSH and VSL is the total VM. So as here to have heavy rate, light rate together, it's give me the total rate. Total rate is coming also from VM, which get it directly from the tool. So this value I don't have any issue here. The problem here how to split. Now it depends on the slippage velocity, and also we have superficial velocity of heavy phase plus superficial velocity flight phase. The sum of the two equal to VM here. So now come to the flow correlation, because we say that's slippage velocity. There is no like equation you can get it directly. It depends on the correlation. Something like some mathematical correlation, some things they do it in the lab. There is different from observation, of course. Let's say here, let's take pipe here vertical, and here we have single phase. Let's say here we have water. And after that, you have some bubbles. Because in this case, they take oil and gas, two phase, no problem. Let's take this blue color, it's oil. All this one is oil. And here I have some bubbles of gas. So it means like small bubbles here. And after that, I have more bubbles. What's happened? These bubbles of light phase, whatever, this gas, in our case, gas, when it's flowing together, it's forming big bubbles. Then here I start getting slug flow. Here I have more, with more velocity, also depend on the velocity. So I have, like here I have pro. Here I have more, what we call annular mist flow. What means you have also in the side here, you have like film of liquid, whatever, like in our case, it's oil or maybe water in the pipe side. And we have like here mixture. And remember that's our tool, it's always in the center. So sometimes even from MPLT, unless if you use like some correlation, which you cannot get like perfectly, especially when you have like annular mist flow, you have some flow. And I remember in this case, Khalid, if we go back to derivative pressure. In some cases, derivative pressure, it gives you more information, because sometimes, let's say, you assume that's your, either you have like nuclear density or acoustic density. From myself, to be honest, I prefer the nuclear density. It's more accurate. Acoustic density or fork density by tuning fork sometimes is not so much accurate, because depend on the frequencies. If you, in some cases, you get from your tool, which is in the center, either FDR or either acoustic density, you get density, let's say, of 0.3, for example, if you have like gas with oil. When you derivate, you get something like 0.45. It means more, because sometimes derivative, it's still the pressure when you make the derivative from pressure, because still this effect of this film, you have it as hydrostatic pressure. So you can get it from the pressure. But since the tool, let's say either tuning fork density tool or either nuclear tool, because it's in the center, and the sensor itself is in the sensor, it's in the center of the tool. So we cannot see this film of water. So in some cases, derivative pressure, it's better than the other type of density tool. So this one is the flow regimes. So of course, here we have different, because also you have liquid gas and liquid. Like here, for example, we have liquid gas, sometimes we have oil and water, liquid. So all these people, they make different correlation. So I think the famous one, it's Duckler. And also this one, the second one, is Agent and Brown. Some other one, for liquid, it's less complexity. Liquid, it's okay. But the problem when you have like light gas and with oil, or with water. It's coming like more complicated. Mainly when you have like gas, it's complicated. It's not same as liquid. So also we can see also the flow regime in vertical pipe. This one it's bubble flow. Let's say this blue it's like heavy phase water, for example. The red one it's oil or either. Sometimes you can get slug flow, and this one it's churn flow. This one annular flow, but you still have like some film in the side of the pipe. So this one it's they put it in horizontal pipe. That's why stratified flow. This one is for the horizontal well. Uh, I think this one it's dispersed because it depends on the velocity of the light. Let's say gas or oil with compared with water or oil. So this one wavy annular flow usually you can get it in horizontal well. This one if you have let's say if you have like I don't know like some with gas with high velocity. Maybe sometime it can push even in horizontal pipe. It can push the liquid side in both. I mean in the wall side in the pipe side. So this is because this one is annular and intermittent, and this one is stratified. But most of it is like stratified and horizontal well. I remember mainly when we ran maps tool. I mean like Schlumberger and FSI or from Sondex. You can see because we have like different sensor which is covering the whole area pipe. You have like multi-spinner, multi-prop for capacitance, multi-prop let's say for I mean depth like for to get like electric the electric, and also for the fiber optic to get reflection of the light to you between gas, and you can see even I think even from the tool itself it can give you like 3D processing, and you can see even the flow regime really in the well how it's flow for the horizontal well. So this one also the effect when you have like highly deviated well, what's happened? It's more complicated, especially when the deviation starts getting more than let's say 25, 30, 35, 45 highly deviated well, because all the water is segregated in the low side, and sometimes it's going down. I mean, if you have like only one spinner, sometimes spinner in highly deviated well, it's not giving you the right. I mean, it's giving the right, but the problem it was affected because we have something which is going down and some flow is going up. The light flow is going up and the heavy is going down. And what we call up and down flow, sometimes it's like recirculating water. So this one is only to give you one example when you have like highly deviated well. Quickly, this one also only when you take this one velocity and this one the hold up, and when we change slightly only you see the profile of the velocity, because for the vertical well it's like in the middle. Now if you get deviation, so you get affected, so it depends on your spinner where it's the position of the spinner. So that's why in this case when you get start highly deviated well, it's better to run multi sensor production logging tool, maps tool, or like FSI from Schlumberger, different sensor with different spinner, different holdups, and all things to get measurement in each section of the pipe. This one also you can see when we get deviated like more deviated well, nearly vertical well. You can see even it's like slightly deviated. This one is highly deviated well. You can see the velocity how it's sent profile. Here all the light phases in the top, and here the heavy phases in down, and you can see even by hold up and profile of the velocity. This one is like horizontal well, you can see the heavy phase in down and that phase, and you can see the velocity of its distribution of the velocity itself. So this one, when you have pure oil and pure water, this one is horizontal. This one is like when you have it in vertical, everything is like it's bubbling. See the good case. This one, when you have like oil and you have like small water, depend on the quantity. Here you have like pure water, and here you like mixed in the top. So depend also between. That's why I want to say that there is a relation also between the hold up and the velocity itself. So this one is coming like more complicated in this case. Sometimes it's only to get because now it's okay with the technology. We have this multi prop tools, maps tools. It's somehow resolving this issue, and you can get uh, what you have as flow regime in your well, because you have different sensors give you, and from this they can generate the velocity profile and give you also like 3D flow regime from the data. This one is an example. I don't know the movie it's still working here or not. Just I want to show one movie. This one you see here, it's like this one is 6,000 barrel a day. This one is total flow rate. This one 1,500. This one 600. But when we say rate, it means now we are talking about velocity. You see the effect of the velocity and also the inclination. So you see here only for the horizontal oil, this one is, for example, it's about 1 degree. Let's say here 91, here 90, and here 89. This one is perfectly horizontal. This one, it's 91 going downward, or what you call, and this one is going up here. And this one, it's 80. So you see here, for example, for 6,000 total rate, almost we have like 50-50 here. Almost this one it's water, this one it's oil, and here how it's moved. This one we have less here, and here it's coming, it's 50-50, and here's the, I mean, in the uphill side, the oil it's coming taking. That's why this is the holder. Now this, you see the portion or the percent from the pipe, how much is occupied the oil, it's small, but you have like high velocity because it's in small area. You have the same rate of oil, but it's in the small area. And water have less. Here it's equal velocity. Here is, let's say you don't have steepage velocity. Here is 0. Here we have something. Here you see the water, it's moving faster because it's like going down 91 degree. And the light phase oil, it's moving slower than the water, and it's occupied more volume. So you see only about 1 degree how it's make difference in the flow regime complete. But because now for the horizontal one, there is like specific tool which we go briefly through it, this maps tool. So it's at least you can get the velocity for gas, oil, depend. I mean, it's not we calculate I think one velocity. So understand an example. So here I want to share with you the effects. If we go back to the spinner calibration, when we talk about the threshold and the effect of the viscosity at this time. So here, this is like, it's a real example, which we can see here, the effects of the velocity. So this one is raw data from a well. What we can see, we have 3 down and 3 up passes. I think at 10, 20, and 30 meter per minute down and up. And here we have the perforation zone. We have like 3 perforation zone. And here we can see the spinner. This is our spinner. So what we can see, it's like spinner. It's normally when we don't have any flow, it's like symmetrical. The up and down passes are symmetrical to the line 0. This one dashed the blue line. So it is symmetrical, here is symmetrical. But the problem here, it's like the spinner is reading less, either in down or either in up. But it also is not in the same. Here, it's like if you see across the perforation, but you see the down one, it was here, the up two, it was here. So it's not, so let's see. Here we can define 2 zones, A and B, it's clear. And also small one, if you see here. Also here, there is like small change here. It's like here small change, and then here, and here is big change. So we have A, B, C, and 3 zones. So for here, if we take spinner calibration, we can take this one, this yellow zone. It's for our spinner calibration zone. Let's make this calibration here. 1, 2, 3. Now we get this, because we have this one and this one is closed, and we have the top one, it's here. And we have all this one, slope and intercept and threshold. So we can see zone A threshold is very high, 4.56. B and C threshold, it's around 1.2 and 1. So if we make, if we process our velocity with the spinner calibration and with the spinner data, what we get? We get this one. We don't have anything, 0. Even here, it's like assuming I have some cross flow or something, but no, because here we have two type of fluid, which we can see it later on the density. Here I have one type of fluid, and here I have one. Here I have water, and here I have heavy oil, viscous heavy oil. So let's see if we take normal. So here, let's now go to the same example. Now you see here it's my density, and here is my capacitance. So you see here, we have almost fresh water. Here we have like sump water. And here we have like heavy phase oil, because I think it's 0.8, it's almost, yeah, close to 0.86 or something like this. And we can see here from capacitance, this is water all the way. And here we have like hydrocarbon, which is oil. But here we have two type of water. It's like fresh water or something, yeah. And here it's sump water. Heavy viscous oil, this one, density of 0.9. Here it's like almost fresh water, 1.01. And here it's some salt water, it's 1.06, something, sump water. Yeah, let's see. Okay. So now we're going to take, I think, one calibration zone, only this one. I take one zone, because before, and I get this one, this calibration. So now I am only using one threshold. I assume that is the same liquid properties, so I don't need to take different zone. I take one zone. So if I take in this case one zone, what's happened? So you see what give me? What means it's like the well is producing from here. I have here 0, because I take this calibration in 0, and here the well is like producing, which is not real.
Farid,
Yeah.
can I ask a question here?
Yeah.
So as I understood, this calibration zone, you were putting in the like zone where to calibrate the spinner. So it will depend on the fluid present and also the how to say the spinner response itself.
Yeah. No, what I mean, like here, because we have, I know this one, because it's heavy viscous oil. So in this case, when you see like there is big difference, let's say if you have like water and light oil, it's almost the same. I mean, it's not affecting, because when you have viscosity, it means threshold is not the same. You get my point?
I see, yeah.
So what I want to show by this example, that's if we use the normal methodology, like one zone here. So now what I get here like I have like production here, yeah, because here even it's around something, yeah, I have here 0, because I take my zone here and I apply this slope and threshold for all data, which is not right. So I get this velocity profile. It's like I have production from here. So now I will I make another example. I will take here on the top, and both cases are not right. So the first one is the right one. And also when I make my interpretation, I get oil from it. You see the interpretation now? Which is not right. So that's why this one is an example. So now let's take now the other zone. I will take this one in heavy viscous oil. I get this calibration. See, calibration, it's okay, but here is threshold. It's 4. Before it was 1 in fresh water. Now threshold, that means it's 4.65. It means my spinner, it need almost 4.5 meter per minute to start rotate. Why? Because it's viscous oil, heavy oil, viscous oil. So what's happened? This one is give me, it's like down flow. Okay, but this one where it's going, it seems like it's going down. I have flow negative. Now I have this one, this picture. If I make my interpretation with this, that's now I think summarize. Yeah. So this one, when I take this one first, I get this one. You see this red velocity profile. Okay, because I say this one is heavy viscous oil, this one is fresh water almost, this one is sump water. So now I will take this one. What I get? I get this one. Now let's take A and B. Let's take, I mean, two different. I get zero. So this is the reality. I mean, zero flow. So I mean, here, the shape of the spinner, even let's say, even for example, let's say we don't run density 2. This one is give you an indication, even from spinner itself, it gives you spinner, it's behave differently. It's reading less. What means the spinner, it's in a viscous liquid. Or so you get my point. Even let's say forget the density here, forget everything. Even if you see only, you see the cable speed, but just you need to check that you don't change the cable speed, but you have change in your spinner readings. And also why? If you can see here, it's matching also. Because when we ran a different cable speed, you see, the liquid before it was here. And maybe because when you pull, I mean, you don't keep the contact, I mean, stable all the way. And also, it's not the same when you run with like low speed and with high speed. But you see, the spinner, it's matching with density, always. So in Amrod, they put now, because I remember when I started using Amrod, they don't have this option, but we do it with another way. Just we expand the zone for calibration. And I change the threshold. I make to consider. But now the good things, they put it now. This one is the mode 1, mode 3. That's why now this one, independent slope and threshold. Used for, I mean, it's used independently, and then you define at which level. For example, I say, okay, you apply this slope and threshold till this depth. From here to here, this area, you apply the other one. So this one is example. This one is usually, I think this one, when you see this zigzag, it's ESP, and sometimes it's beam pump well. I mean, it's pumping in this well. So that's why you see this fluctuation, because the pump, the effect of the pump. And this one, I think, is slotted liner. So just an example to see, for example, here it's like most of the water is coming from here, and you can see also from temperature, from capacitance, and even you can see the pressure here. I don't know this one is ESP or beam pump well. And also you can see it even in the station here. This one is like slotted liner. They make like here, what they call zip bucket to isolate. So this one is an example how to get all what we discussed it before. We have like spinner, of course, from the spinner, and you have like speed. So from the spinner, we can here generate. Here we take two zones. We can generate fluid velocity. This one, which gives me VM, and then of course we take temperature, pressure, and capacitance and density, and we can get this three-phase here, because here oil is in red, oil and water. You can see that's the bottom zone, most of it is water, but the oil is from the top. And also here, also they have this relaxation, like you can see also the effect of the water. So this one is an example. This one also another example. This one is different perforation. Also, I think this one is DL completion. I think this beam pump or ESP. Because when you see this, also this one you can see it from temperature, even from the bottom. It's like there is like water is rise, water canning or something. See the compared to the geothermal, and you can see the top zone. It's because I think this one is different reservoir. So this is data, yeah. This one also the same things. It's with the well with like pump. You see this fluctuation. But you can see what I want to say from those examples. Even sometimes if you see the raw data, you feel that's, but you need to understand, I mean, the well condition, because you cannot get better. This is the well, how it's flow with this beam pump or ESP or whatever. You have these things, cannot do any things. Just you can see here the overall, I mean, the average, it's clear here, total, and here you have like flow, it's coming from the bottom, and here you have like some flow. I mean, because here we don't cover the bottom perforation, but what is coming as production from this two bottom perforation is this. So this one is like with high BSW, what they say, or water holdup. This one, yeah, I think this one it's during shutting. And the well is still because when they closed the well, I think even they shut it for I don't know for how long, but still we have because we have different reservoir, we have cross flow, so we have like water flow from the top and it's going down. Here also the same things. It's when all this kind of well, this one it's I think this one it's oil well. This one it's yeah oil. We have two phase, oil and water, first and second rate. This one is light oil well. We have downhole the oil is in red, and so we have free like here from the bottom one is most oil, and the top one we start getting free downhole gas. This one you get it depend on your PVT, depend on your bubble point. If you change your bubble point, maybe this green it's disappear completely. So that's why the PVT is very important to get almost. I mean something that's can I say at least to be like close to the reality. It's not something completely wrong. Otherwise, you get your results wrong, and maybe your clients come to you, your interpretation it's wrong, but reality because what they give you in the beginning as PVT it's wrong. So it's coming from the side. So you need to understand. This one also, I think it's an example, yeah, from first and second rate production profile. You can see also yes, the same case. So this one, I mean, here we can get the what we call SIP when you make like two rate production profile with shutting, and then because you have pressure and you have rate, and then you can get IPR, your IPR. This one, it's see the utility of the production logging is to compare. There is like pre and post simulation production profile. Here, I think there is a job. This one is pre and this one is post. They make acid job. This one it's horizontal well. You can see the well trajectory. This one horizontal, but because since the downhole phase, it was like single phase. It was light oil and high rate well, and also because it was cased and perforated. So that's why even the standard production logging it's work in this case. It's work perfectly, no issue. So we can see they make, I think, they make like acid job. This one is before stimulation, this one after stimulation. If I remember, I think, yeah, you can see the increase in the rate. It's clear. I think they do it in the same shock size that they get because they bypass the skin and they make like cleaning. So we have like more rate. And we can compare here and here just to make like comparison table to see the gain in the production between and before and after. So we can see that's here, except here something I don't know what's happened. It's almost the same in this area, but in the other the effects it's mainly here more effect on the bottom. This acid job it's clear, even you can see from the profile. So this is one of the application of the production logging. For example, like here, they do one before stimulation job, and they do after another one post job, and we can present something like this. And after that, of course, the team, reservoir, and the geologs and all the team, they can know the effect of this kind of stimulation. Maybe they want to do it for more wells, and so it's good to know what we are doing. It's like experiment. This one is gas well. I think with it's not very high. This one also we let's see. Yeah, this one also it's gas well. You can see we have water production is not from the bottom, but from this. It's coming mainly small here from here, but also from the other zone. This one is yeah. This one is complicated job. It's not complicated, but this one is with the after nitrogen lift because this well is like depleted and it's not can maintain for long for production. So they do the lift, and I think quickly after we do the production logging. So this one, why I put it even the data, it looks like some kind of rubbish, but this is because it's like already depleted well. So just they want to see. Maybe they want to make any to program stimulation job or I don't know, but we want to see what's going. So even so here, even you can see even during the station, but we can see clearly that's the most pushed from here, and also you can see here. So that's what I mean. Sometimes even when you see the data like this, sometimes that's what you can get from the well. Just try to get something from this data. Can see the overall picture, and of course taking in account the well condition like here for example after lifting with nitrogen and where it not can sustain for production for a long time. Just like to take snapshot in short moment. Also this one you see, for example this one also, because we have this what we call liquid loading as well, was they are suffering before. And you can see even here from the density here. The things from density here, you can see clearly that there is an increase from here because we have water, it's going inside. And of course, this water sometimes is not also flowing like smoothly to the surface because it needs certain gas velocity and gas to be able to lift. Sometimes part of it is fall down. But in our case, I think it's okay here. But we can see it also here from temperature. You see that temperature here it's increasing since the water is coming from here. Of course, because after that we have like more gas, which lift also this water with it. But because there is two different reservoirs, this one and this one is still. But also from the temperature is give indication maybe this water is coming like what we call finger through up from deep zone or so. It's also
Sorry, Farid, this density, the blue density, is it
yeah.
a tuning fork density
No,
or
no, no,
nuclear
no.
density?
This one is the yeah, it's tuning fork. Yeah, tuning fork.
Yeah,
This
I think.
yeah, FDD yeah. No, no, but the density itself it's okay. Even I don't know. Fortunately, even if you see the pressure here, even the pressure it gives you an indication that there is this. Even from the pressure, from capacitance, from many things. I know that. Yeah,
Okay.
yeah, but it's interesting because here, of course, this is because this two different reservoir they are not connected. But also you see, because you see from density and also from temperature here, and also from the other things. So you see clearly water is coming from here. Even here, it's almost, because even you see like you have more gas here, but like because the volume of water. So here also time-lapse production profile. This where they make different. We make different production of here, 2014, 2015, because first of all they start here, they make in this reservoir, they produce, and after that, uh, this one 2014, yes, and after that in 2014, okay, they add this perforation, and what's happened? They have cross flow. So what I mean from this time lapse, this is one because at the beginning of this presentation we talk about the application of production logging and how it can help to understand more our reservoir, our wells, and what we can do better. So the time lapse sometimes is to bring like the whole image. I mean, it's like puzzles, and you want to put it in one view. For me, really, it's good to get like combine information in one plot. It's give you like the full picture in one go. So that's what happens. So they start producing from here. Maybe they depleted this reservoir. After that, they make perforation, and they start getting production from here. Either they start getting cross flow in this area. And this is the last one. This one is flow December. The well is completely خلاص depleted. You see small this one with the thing. Yeah. And also here you can see the density. What's happened? Here the temperature. Here also you can see the pressure. And here you see the water. Well, they start the water December because this one all this problem from after that one start getting water, they get small gas. So this one is just I want to show what means time lapse. So you can see like in this plot, maybe with few comments even in the plot, you can tell the whole story of this well since they start and the perforation. You can make like a summary and then you can get like clear picture because sometimes they understand why my well is like depleted like this or why I have a drop in the production. So if you go back, you make the front and you see the series start cross flowing like this area. خلاص, it's already completely depleted. This one also it's gas well. Because I think there is other example. I cannot make it this time. Maybe later on. But this is overall what we can get from the PLT. I think we finished with the multi-phase. I know that's I'm going fast somewhat, just we want to close. But anyhow, I share with you the whole presentation. And anyone from you, and keep free to ask me any question at any time. Just you can through LinkedIn or through my email. I don't mind. You have any, or if you want to have any data I want to discuss this. But this one is overall for the section for the day. I think only remaining now selective from performance. I don't know, Khalid, if we can go through it and then we keep the question to the end as Saleh she request. Because this one, to be honest, I know maybe your side, maybe from your side you are more in this kind of tests. The idea for that is to get the relation between rate and pressure and to know the absolute rate from the well. And also you can know if you want to produce how much you want to put downhole pressure. So you can adjust your choke. It's give you an idea. So this one is it's one of the tests. Mainly they do it at the beginning when the well starts flowing. It's better. We can go quickly through it, no problem, just to give an idea. So of course, in this section we have like
Farid, just
different, yeah.
small comment. We are tight in time. Maybe if you, I don't know if you want to make it another session, or maybe we can go through it
I think
fast.
no need. We
Yes.
can go quickly now
Mm-hmm.
because even me to be honest, this one is the rate, this one is the pressure. This one what they call conventional backup pressure. I mean, they start with high pressure and then they start releasing the pressure. I mean, less pressure, more rate. This is one type of test. Sorry. I think there is this one what they call isochronal test. I think that's what there is. So I mean the period. I think in this test the period of flowing it will be equal, shutting and flowing. They open and then they shut. Flowing to shutting one, shutting two. The period will be same, and flowing same. This is another type. Of course, in this we do production logging. This flowing, for example, flow one we do, flow two, flow three. So this is way another isochronal test. This one it's the log of my. Sorry, this one they call it modified. This one modified shutting, I think, and flowing the same period. I don't know who decide this one. I think also reservoir engineer and PT, all the team, they will decide. Depend on other things. I think the maybe permeability, maybe also the different thing. Normally they should do it with the proper way. I remember only one time I do it. There is one well because this is the I mean the idea bottom hole pressure layer, and you can see, for example, if you have different layer, because they can do that APR with from surface well test, but only for the gross, for the total. The advantage from production logging is we can do it by layer, and you can know every layer, each layer, how much it's producing, and at what pressure it can cross flowing also as well. So this is the idea. So of course we have, if we have like liquid, we have IPR straight line. But for gas case, gas, this one, the equation for the straight line, productivity index is the rate divided by delta pressure. I think it's and this one also, what we call, this one is straight line. This one is the other. I mean, because mainly for gas, you cannot use straight line because the gas is compressibility different. So we have, I think, Vitkovich, and we have another type of. That's what we have with Amrod. I think there are many different type. But what I mean here, because this one also is relation with the Darcy straight line. This, yeah, LIT and A and B, and there is another one for C. So you can, with a road, you can use three of them. This one is the simple one. Let's say if you have like liquid oil, or let's say you have water, injector water, it's straightforward. Even if you apply this one, it's give you an idea. But this one, it's mainly for different phases. So just I want to, yeah, the idea to get absolute outflow. It means if you make like complete drawdown for your reservoir, how much you can get as rate. Complete drawdown, they call absolute outflow, deliverability, maximum flow what you can get. Because maybe you cannot do it, but from this multi-rate test, you can know how much you can get maximum from your well, depend on the pressure. Also, you can get your average pressure. I mean, for each layer, you can get like the reservoir pressure. Of course, it's estimated from this correlation, ATI or straight line, because it's the relation with the Darcy law. So you can get your absolute pressure from this to the boundary. So this one is quickly okay. So this is real data. This is the real data. So you can get AOFP, absolute outflow. This one is condensate gas well, million meter cube a day, from this layer, from this layer, from this layer. You can get also your C and N, because here we have to use C and N, is not FTA. You can get average pressure. You can get what we call corrected. Here in software, you can put in the same depth. You tell the software, you give me the pressure, for example, at 4,000. So it give you like, even the layer, it's like, it's not in the same depth, but it's take the offset. It give you like, it's. So here we, this one is the composite. This one is the first layer. This one is the second one. This one is the third one. So, and this one is the real data. When we put, of course, they are not doing it like this isochronal exactly, because here we stay for longer. We do the first, I think this is the first flowing, and then this is the shutting, the second, third, and fourth. Yeah. And this one, this is the pressure, and this one is the spinner. Somehow it's our rate, because spinner is velocity and velocity is rate. So this is the 4 rates. And this is the velocity, of course, from both ILS and spinner. You can see the velocity, and you can see also here the temperature. You can see the density, and you can see the pressure. So of course, for IPR, we need here the rate and the pressure. What we have it here. So we have here. So this is the rate. During shutting, we have small cross flow here. During shutting, this is the first, I think first, second, we make 4 rate. And we have pressure. So that's what you need for this SPA. And you can get this one, the rate, on the top, the pressure and the rate, and also the survey. And here's the shock size. This is the composite, the total, and this is for the top layer, the middle layer, and the bottom layer. Yeah, so this is the output. So, I mean, if you have like this multi-rate, you can get the reservoir pressure, the outflow, absolute outflow rate, and also you can get like your reservoir pressure, average pressure, what they call. Even if it's say, it's like you are doing modular tests. It's not,
Yeah.
I mean, direct measurement, but it's give you something closed. And sometimes you can see it, even when if you do it the correct way, you can see it. That's true. The area, there is a, I mean, the unit of the reservoir which is cross flowing, you get less reservoir pressure compared with the other layer. You can check.
I think Farid, this is a great application for this kind application, this SIP, because we can measure the pressure in each layer, like not
Yes,
measure, we can estimate. I mean, yes.
estimate, but they should do it, I think, with the right way for the type of test, isochronal or equal time. They know the area. I know here this data. I get it because there is one guy. Maybe he tried to do it with the proper way, but sometimes if only they close and they open, I mean, they don't respect uh, the sequence.
Hmm.
You can get something. You still you still get like pressure, and you can confirm it with the cross flow. You get something. That's why when you make multi-rate, it's better to do it to the proper way, and you get like because you already spent time and spent money to make this survey, production logging survey for different phases. So I don't know why you don't. I mean, at least take this application in advance to get like your reservoir pressure and your absolute outflow.
Yeah, actually, getting the
Yeah,
reservoir pressure is a major thing in
yeah,
any reservoir engineering study or any field development, like how
yeah.
to say sequence. Okay, good.
So that's is. I think this is the whole things for this presentation. Just we want to go through. I mean, we want to put everything related to the production logging, starting from the sensor to the spinner. Maybe you focus more on the spinner calibration. Multi-phase also, we know the definition of hold up and slippage velocity and the correlation and how we get the multi-phase interpretation and the parameter, I mean, related to this with PVT, all these things. That's
Mhm.
how we make our interpretation from all these things. Of course, there is like a lot of details. We cannot cover everything in this presentation, but maybe later on we can like make like specific subject. Why not to take like example and go through it
Yes.
for more understanding?
Yes, that would
So,
be great actually.
Yeah.
to our participants, feel free to ask question if you need directly. So, I think there is no question.
I think I have one.
Okay.
Farid, just want to ask you this question. Maybe it's not covered in this presentation, but I wanted to know if if we can get something related to the reservoir pressure from the noise. We can do it or no?
Noise tool
Yes.
from I mean SNL.
Yes.
To be honest, SNL, I don't deal with data SNL so much. So maybe you are in the best position to answer this than me.
I have hints, but I don't. I mean, I am not into it like very deeply. But I want to. Maybe I thought you'll have an idea or something.
No, no, to be honest, no. Because I know from PLT, if you do multi-rate, okay, you can get this average pressure and this, because you can get it. At least you can get like estimation. If you do your test with the proper way, you can get.
Hmm. Okay, then. So, if there is any other question, I believe we can conclude
Me,
these
I want
sessions.
to
Saliha.
request. I want to request something from Monsieur Mekhzoumi. Mr. Mekhzoumi, if you can
Right.
prepare other session for us, but about well testing and their application.
Well test. To be honest, I'm not well test guy.
Yeah.
My background is okay, petrol engineering and overall. I work in logging. I mean, log analyst, petrophysicist because I start with open hole,
Mm-hmm.
and also my background because we I work in Hassim Saud, was doing witnessing operation of logging with I mean Schlumberger, Baker, Hasp, Aldia before.
Mm.
Uh, After that, I was more specialized in case door, let's say production logging. Well test, I will try to find someone who I know someone who do a test. I can give like small presentation about well test in general, but I think it's better if we can get someone well
Most.
test guy who can do the whole yeah.
Okay, thank you very much.
Because why I'm talking about well test, because usually we deal with well test. Usually
Yes,
we make PLT and also
in the
well
same
test
time.
in the same time.
Yes.
Yeah, yeah. So no issue. Either we can make like small simple thing, or either it's better. I know someone. I don't know if he agree. If he can present for well test, or maybe Sukhal he can look for,
Okay.
because
Yes.
well test. I mean, in general, it's okay. It's to make like to separate the phase and then to quantify the quantity. But
Mm.
also in well test there is like different type of test. There is different different way how to test. Like for example, like this multimeter VX, it's same as our tool. And there is the standard well test when there is like separator and they make the separation. This is the more accurate. And also there is this multimeter, small. I mean setup. They put it even in the wellhead, or because they using this for VX. They call it VX before. They calculate the velocity for each phase using radioactive source, and they need calibration. It's the same way. It's like how we are doing interpretation.
Mm-hmm.
Mr. Farid, I'd like
Yes,
I have a quick question about maybe an idea to introduce or give an overview for well test. My question is how to use well test to estimate reserve in place or hydrocarbon in place, especially for exploration.
yeah,
Because we don't have many data, I would like to have an small method or quick method to how to use the data from well test to estimate volume in place.
yeah. Because when say what test, sometime usually in exploration, what I know they use also they use drill steam test, DST.
Yes, yes, from
Yeah,
DST.
yeah, DST, of course. They engage bottom. Sometimes also I do it myself. Sometimes we do a PLT through the DST string itself. We do it many times. I mean, they have like surface well test. They have gauge and I cannot say permanent gauge. I mean, the all sequence when they shut the well, when they flood the well, to make this PTA for from gauges. Yeah, and also from our side we do PLT. Yeah, it's the whole things. Of course, it's to calculate, estimate. I mean, the reservoir capability and also to quantify.
Yes,
Yeah,
Yes, Farid, we really thank you and for the effort and the
thank you,
very
Farid.
informative presentation from first or second or third webinar. We really appreciate your effort and time, and we hope to get you in more like upcoming session, inshallah.
Inshallah.
Uh, I don't know about the audience. Maybe someone has a question now, or we can. I believe that's it. Okay, then thank you so much all for attending. Thank you, Farid, again for the presentation. And have a, how to say, if you are in evening, have a great evening. If you are still in daylight, you have a good day ahead.
I think
Yalla.
it's a new day.
Yeah. Assalamu alaikum. Yalla.
Thank you
Salam.
very
See
much.
you
Okay,
all,
thank
inshallah,
you for
بخير.
everyone.
Yeah.
Shukran.
Thank you.
Thank you.
Assalamu alaikum. Bye.
Assalamu alaikum.